Okay, so for today is first of all, I want to actually talk about not so much of the derivation of the first homework question that I will just do, but a little bit of the implication in the hierarchical setting, okay, that we have seen so far. So what I'm gonna do is, give me a second, sorry. What I'm gonna do is I will try to sketch the different relationships and then show you why in the hierarchical setting the variances and covariances depends on what you're conditioning, gonna look very different. Okay, so post the solutions later after class, but before, okay. So if you have done it correctly, you will see that the variance of Yij given theta j and sigma j, this should just be sigma square, right? I mean, because this is, yeah, the door is a little bit weird today, so I can do it open. Yeah, so this one is the most straightforward one, right? Because think about, so I will try to draw the hierarchical model that we have seen before on the other side. So what we know is all of the y, here I will use j. So because of the hierarchical nature, you will have its mean. And all of the mean comes from the same normal with mu and tau square. Okay? And down here, this is the simpler case where you specify only one sigma square. Okay? So if you think about, okay, so this is the most straightforward one to get, I think, right? Because now you're conditioning on the immediately, so one more thing, Yij is a normal from theta j and sigma square, right? So because of the model, the normal model in this way, so we know that this should be sigma square. This is the most easiest one, I should say. And then you were asked to show something extra. So the first one is the variance of the mean, the sample mean, okay? So if you do it correctly, you know that this will be sigma square over j and j, okay? Sample mean, the variance of it should be, say here, the population mean divided by the sample size, okay? All right, and this is, again, central limit theorem, et cetera, all related to this results if you're doing normal, okay? And the last one is the covariance of two, let me get it right, of two observation in the same group. If you are conditioning on the group mean and the overall variance over there, this will be 0, okay? Because they're independent IID from the same normal. Okay, so this is what we know. Okay, so the other half, you notice that because the question asks you to do 3 for each set. The second set of all of this is not conditioning on this ones and this ones, but rather conditioning on this one. Okay, so it's not as straightforward as before, of course, and that's why those iterative formula are there for you. So let me actually write them out first, the results. So if you have done it correctly, in the hierarchy, once you don't condition immediately on the thing that in the model, but one step lower in the hierarchy, you do this, this actually going to give you sigma squared plus tau squared. Okay, and the second one, the y bar given mu and tau squared will be sigma squared over nj plus tau squared. Okay? And the last one, two observations from the same group, even this will be tau squared. Okay, if you show it correctly. Okay, but so solution I will post it so you can check how to show it. But I do want to take the time to discuss what are the implications over here. So obviously this is larger than sigma squared, right? So the variance that you have conditioning on mu and tau squared comparing to, over here, sigma, theta j and sigma squared, this one going to be larger. Okay, and similarly, this one is larger than, and this is not 0. Like this is larger and not 0. Okay, so if you actually read the question, I only asked you to do part C, but part A actually push you to think which variance or covariance is larger, right? So let me, if you have your textbook, you can bring it out, but I can read that part for you, because questions like they have, which do you think is bigger, this one or this one? Okay, I mean, of course, we show it mathematically that the second one will be larger, but they did tell you a way to intuitively get the idea. To guide your intuition, you can interpret the first, which is this one, as the variability of all of the yi's when you sampling from a fixed group. So this is what that is. You're sampling from a fixed group, because you know you're conditioning on the group mean and the variance. While this one, you're sampling the variability not only from the first group, right? But also you have one more layer of the sampling that each of the mean is from another normal over here. Okay? So in a sense, you see that, I mean, I think it's not by chance that this is like the variability of yij given mu and tau squared is actually sigma squared plus the tau squared, and that tau squared is the variability of the normal that you have. Okay. So first of all, this one will be smaller than this, even before you show it, because this is only looking at the variability that you sample from a particular group. That's your sample model. But this one, because you're not conditioning on theta j and sigma square, you're conditioning further on the other hyperparameters in the sense that this mu and tau square is what the normal distribution that the theta are going to follow. Okay. So you see this combined effect in terms of the variance. Yes?
One thing I don't quite understand is why, what gravitationally, like, I think you just answered this a little bit, but why I get condition on mu and tau squared. You need more information to actually draw a yij. You can't, even if you draw a theta j from mu and tau squared, you still need sigma squared to actually draw a yij. So I don't understand how that is actually a meaningful method.
Okay, so Eli's question is, say, in order to draw a yij, say here, this is the sample model. So you know that you need to draw from theta j and sigma, theta j and sigma square over here. But if you're only conditioning on mu and tau square, you still need the sigma square to sample from that, right? So my take on this, I guess the super clear, correct way to write it will be actually still conditioning on sigma square over here. But the big difference between these two is trying to think about whether you're only conditioning on the mean, the group mean, or you go one step lower to the hierarchy that you know that I'm not conditioning on the mean, I'm actually conditioning on the mean and variance of the distribution of the mean. So you have one more layer over there, but you're right. I think to actually do everything entirely correct, you will need to have sigma square. Let me rewrite over here. Sorry, the angle. You need to have a, oops. You should have a sigma square over here. Otherwise, you won't be able to sample it, right? And you actually can see that it is, I mean, once you do all of the iterative steps, it is there. But the focus here is talking about the effect of the mean and the variability over there. Make sense? Yeah, so I mean, yeah, then also if you look at the X bar, like the sample mean, if you're only conditioning on the group mean and sigma square, this will be sigma square over nj. But if you also, so here again, you need to have a sigma square, just as what we were describing earlier. But you see that the variability, you have one extra variability coming up from this tau square. Okay. And the covariance works in a similar way, especially like this covariance, if you're already conditioning on the group mean and sigma square, because they're IID, the covariance is going to be 0. So there, you can say yi1j and yi2j is conditionally independent of theta j and sigma square. You might have heard terms like this before. But if you move over here, if I condition on the hyperparameters, mu and tau square, they're not conditional independent anymore, which makes sense if you think about it. So if you look at the graph, so that's why I really like keeping hierarchical model in a graph sense. Sorry, mostly this part over here. So what we're talking about, the covariance to be 0 here, meaning that, say, in one group, I got number 1 and number 2, right? So this is saying that conditioning on the particular theta j for that group, these two observations, and of course the sigma square over here, these two will be conditionally independent, okay, because they're IID, right? But however, if you move one lower down of your hierarchy, even though conditioning on theta j, they're conditionally independent, but if you think about up further, I should say down, in the hierarchy over there, because all the mu and tau square, both mu and tau square have effect on all of the j. So once you do that, you'll realize that they're not conditionally independent based on that. Okay? But of course, the whole exercise is only looking at, say, 2 observations from the same group. You can also do that for, say, any random two choices of 2 observations from across the group. Then you will see different pictures, of course. But the general idea is there that the variability of all of the model, like of the entire model, is actually introduced at different levels. And you have this like added effect in some way. Okay? And for the normal case, it's actually easy for us to show what it is. Okay? Yeah. So that's mostly what I want to talk about. And all this say, I should also say, like, you have this y, and then y is from the mean of the theta, and theta has another normal distribution. All this added effect, especially if you move to like regression, as well as in particular those regressions for time series, you will see a lot of similarities over here, in a sense that over here we're doing observation to be normally distributed, and then the mean of the normal distribution going to be again normally distributed, right? So the other part of all of this I want to talk about is what we just seen is you have yij is a normal theta j and sigma square, and then the hierarchy that we have seen is that the normals theta j are gonna follow a further normal down there. So you see that like it's a normal nested in a normal in a sense that the variability are introduced in 2 levels. Okay, so something like analogy that I want to make is I just show you like the setup, and this is related to regression, what we're going to talk about today, but not as complicated as the model that I'm going to show you here. If you have, I don't know, taken some courses related to time series or like that kind of data analysis, you might heard terms like dynamic linear model. I just want to show you what it is and then how the analogy is there. So for dynamic linear model, what they're doing is they assume that your observation, now all of the t is a subscript of the time, okay? Yeah, so here you're gonna do your observation of time t gonna be some mean at time t plus the error. Okay, so this will be a typical regression setting that you might have seen before. And the thing is, a lot of times in time series, they try to assume that for the mean, there will be some time dependency introduced. Okay, so for example, the simplest dynamic linear model that they do will be my current mean gonna be a sum of my previous mean plus some error term. Okay, so here, this error term, they put a different normal, not standard normal, but normal mean, 0, and some other variance over there. Okay, so if you think about this, I mean, I wouldn't say they're exactly the same, but to me, a lot of times, especially try to do the derivation and think about the variability, you will see that for a dynamic linear model like this, observations are the y's, and they assume that you have an underlying process that is time dependent. And then of course, at the observation level, you have some random error. And then also in the underlying latent latent level, you also have some time random error. Okay, so to me, a lot of times I would think of this is another normal, because if you rewrite this will be normal mu t and vt, right? And this will be mu t given mu t minus 1 to be a normal mu t minus 1 with a different variance. Okay, so you can think of this as in the underlying latent level, I have a regression, okay, but time dependence regression over there. And then this is going to be a normal. And then my actual observation is going to be another normal that the mean going to be affected by the latent situation. Okay, so if you actually derive it, I mean, I just want to show you, I mean, I don't remember exactly what they are, but if you actually try to get the variance of yt, you will see that it's going to be the variance of the vt plus the variance of wt together. Okay, you can think of this as nested normal in some sense, that the variability is added up in multiple ways. Okay, so the hierarchical modeling that we have seen, it's more like it's set it up in the hierarchy and then you are introduced in that way. But in a very typical time series model over here, say the dynamic linear models over here, that kind of added effect of the variability through the different levels are also there. Okay, so just want to show you because some of you might have similar stuff before, but of course, when we're doing the Bayesian linear regression, we won't go into detail of like complicated models like this, but it all follows the same idea that you were just doing extra over here. You have one more layer over here, but each of this is a regression in some sense. Okay, all right, so this is what I want to talk about at the beginning, and that took 20 minutes already, but for the second half of this, I would like you to first of all sit together with whoever you did the case study with. Just gonna talk for 5 minutes so everybody's on the same page. And then I will ask you to sit with two other people with two other groups, I will have to figure out how that can work. And then just, you can, each of you will get the chance to talk to the other two people who are not in your group, what you did before, and then in the end, I will bring it up as a whole class. So first of all, just sit with whoever you did the case study with, and then talk. Okay? Yeah. We're just gonna do this for about 3 to 5 minutes. And then we're gonna change, so you get to talk to others about your
So you're just gonna have 3 different normals that I get so nervous when all the pressure's on. I didn't. Yeah.
It's just a default.
These are like technically, so you know, yeah, but you want to so this was the least from the decade. Yes. Oh, you know what I did? I thought I fixed this. There should be some kind of This was with actually I don't know why. Yeah, and see, this has something like borders. And I don't think I have that word like that.
All right, yeah, so if we can now, I don't know how to do this, but just sit with two other people who are not on the same team. Somehow we can figure that out as a group, I think. Just, yeah, like, say like each group, one person stays, and then two other just moves to somewhere else, and then, yeah. Should be able, I didn't count, but I should be able to do it.
Yeah, that's sort of an hypothesis. Like the day that you have to like it's just not only natural, like, yeah, I thought, I mean, what we got was here. I don't know, I think our prior to that, we did get it. Our rules are right. Yeah. Okay. And then assume that the ratio is. Okay. We assume that there is. Fair enough. Yeah, yeah, it's so small. It's the only greatest side of the rest of the really fucking
Okay, so I mean, I have everybody's post on my computer, so I'm happy to bring it up. But we can also, I mean, someone or some of you want to just talk about, say, what you did and what was the biggest difference or similarities that you heard based on a discussion, and then, yeah, that's pretty much it. I mean, there's no fixed answer, but I saw majority was doing normal, right? The normal model. But I did see some other type of model. So yeah, happy to talk about all of the implications, what are the assumptions, why you chose that, and what are your results. Yeah, I have to hold this around, so let me know if you want to talk about what you did, and I'm happy to bring up your write-up over here as well. Sure.
I did it as a normal hierarchical, but would it have been possible to have done it as a multivariate normal? Like, how would you do that?
How would you do that? So first of all, is the data, okay, so maybe let's talk about the data set a little bit. And I'm happy to share something that I did. And okay, let me do it one by one. So something, give me a second. I have it, can I have it over here? Okay. Okay, let me show this first. Because I was trying to do some exploratory data analysis. So I wanted to see how it looks. Okay, let me see, right here. Yeah, so I did some kind of, I mean, not inference at all, just to plot the data in certain ways. So first of all, the data is univariate, right? I mean, you only have, say, two variables pretty much. You have the year, and then each year you have a marriage rate. Yeah, so I agree that we learned about multivariate normal.
I was just thinking you can turn it into having three variables. So like, instead of this year, it's like pre-World War II year, World War II years, and post-World War II years, and have Y1, Y2, Y3.
So what are the Ys?
Like each, so the rates for before, rates during, rates after. Yeah.
So you're adding two variables.
Yeah.
Okay. What do you guys think? Like multivariate normal in what? I mean, let's see. in class, what we did is a specific case that you're looking at student score before and after, and then like multivariate normal in the sense that we're looking at bivariate because you believe that each person, like the pre and post, will be related in somehow. So you're doing that, yeah. But what do you think? Like in this case, yeah, of course you can add more variables based on some extra information or some external data that you can do. But how, if you do it, what does it mean and what's the implication? Are you trying to say something?
I retract my papers.
Okay.
Sorry.
No, that's fine. Okay, so we had a question about multivariate normal. You can respond to it, or some other some other topics related to the example. Yeah, maybe.
I feel like it doesn't really apply very well because I feel like there's not as much of a relationship between the before and after as there would be in like a test control study or something where it's like the same group of people. So I don't think I would use that.
Right, so the multivariate normal example that I gave is specifically good for a bivariate normal in the sense that you have each person's pre and post score. So of course, naturally, if you want to generalize any kind of multivariate normal model, you can do that. But actually soon, when we start talking about multiple linear regression using Bayesian methods, you're going to see multivariate normal again. Because over there, they're looking at all of the, say, like coefficients jointly together, distributing as a multivariate normal. But in terms of like other applications, I would say, of course, if you have like person or individual kind of pre-post kind of score, that would be good. But also, let's see. I think it really depends on how you imagine the data would fall, or how you imagine the joint distribution of multiple variables. So in this case, my take is similar to Katie as well, is you will have to say create a new or multiple new variables to make it into even, because think about multivariate normal, you're doing, say, if you have p number of variables for one observation, and then you're going to do like a p by one, they jointly follow a multivariate normal distribution with dimension p. So over there, if you think about how your data arises, you're saying that for each of the observation, they have the same number of variables and they all should have the similar structure. So I think in that case for here might not be a good fit. Yeah. Okay. Cool. Anything else? But actually, if you move to case study 2, that's something might be useful with multivariate normal. Yeah. Anything else? I mean, back to this. So what I plotted over here, I mean, this is really rough plot over here. I was doing the rates against here, and I just did the 2 vertical lines over there to show that the start and the end of World War II, just to show like the change. And then also down there, I show just calculated, break it into 3 different groups. It's kind of slow over here. Give me a second. If you look at this into 3 different smaller periods, you can return the mean and variances of each, and then you see some differences, but whether those differences should push you to think about a different type of modeling. Or I think some of you, because earlier I was talking to Rachel, she was doing a hierarchical modeling with the normal, but then instead of drawing from the same normal of each of the mean, I think you're doing, you put them in 3 different decades, and then you draw 3 different normal over there. So I guess that seems to be a common approach, or no? Or anybody else? I mean, I've been talking, but what you did and what surprised you by the other people's approaches? Or just tell us what you did and what are the results. Yeah, Katie.
We did it by before, during, and after.
Mm-hmm.
It's supposed to technique, but we did like multiple normal models.
Mm-hmm.
We assumed that the variances would be the same. We didn't do different variances,
Mm-hmm.
although that's like definitely something to think about. But if you compare our final
Mhm.
plot of the
Yeah, let me
posteriors
actually
to
bring it up. Yeah, keep going.
some of the groups that did varying varying variances, they look pretty similar.
Okay.
And we basically found that the during the war rates were distributed with a mean that was a lot lower than the other
Lower?
two groups.
Okay. All right. So let me bring Katie, Ring, and Derek's right up over here. So I guess we can. I guess now it seems that everybody was doing JAX. So I think we're good to read the code really quick to understand what the model is. So it looks like you break it into three, right? Like three groups, periods, before, during, after, and create a new variable over there. And then let's look at the model. So it looks like here you create a new, because of the new variable that you created. So instead of drawing, like the indicator is not for each year, but the indicator is for each time period. Depends on whether it's before or during or after. So this is the biggest difference from the previous, like comparing to the previous modeling that we have done, right? So here, instead of like a school or like a year, you're doing time, and that's the new variable that created. Okay, so this means it's still a hierarchical model, but you're breaking into three different groups in the way they're doing it. But ultimately, each of the mu j is still from the same mu, right? So at the lowest level, you still have the same mu over there. All right, so priors, et cetera, things looks good. So let me go to the results. So here, let's see, do you want to talk a little bit about any of this? So trace plot. Look, okay.
I don't have much to contribute.
Okay, all of this should be fine. So, okay, so you're printing the mu's as well as like the trace plot over here is the three group means, right? Yeah. Okay, sounds good. And autocorrelation looks fine. Effective sample size, okay. And these are the posterior and data.
That's the good one.
Okay, rates in different time periods. So 3, and this is the posterior. Okay. So you do see the before is somewhere in the middle, right? And during is much lower, while after it's yeah, it's really hard to guess what was the reason why. If you think about like before and after, say like doing, of course, makes sense to have it low, but like to compare before and after, it's yeah. In this case, the posterior they look very close. So okay. All right, so okay, so I guess this approach is probably the same as what Rachel did, but anything else? Anything else that you did?
Did you say we put a group before and after in the same group?
Oh, you did that?
No, I was.
Oh, sorry. Can you say that again? You were saying that put 2 in the same group?
We were just saying that before and after that we put in the same group.
Oh, okay. Yeah, I guess that would be another way you can consider it, right? Like especially from here, even if you do it in 3 different groups, the before and after are kind of similar, and you gain some larger sample size in that case. Yeah. Okay, so I guess that's another approach. Anything else? I mean, I'm happy to go to Moodles again to see other comments. Anything else? Irene, so let me, which group you're in so I can bring out the
The
results?
thing you just showed.
Oh, sorry. Oh, okay. Yeah, go ahead.
But I think for Elisa's group, I think we had the same model, but like we had different conclusions about the mean.
Oh, okay. So Elisa, which group you're in so I can, Eli's group? Which Eli? Oh, okay. Okay. All right, so let me bring that up and great, share screen. And then, okay, cool. All right, so what is the, so you're saying that in this case, you're doing a similar approach, and, but what is the difference?
I think we have different conclusions about for the sixth question. Just
Oh,
last
the last part, okay. Oops, okay.
here.
Mm-hmm.
They check the HPD intervals. And they failed to conclude that variance.
So what are the HPG intervals? Maybe at least or Eli, you can, like, what are the HPG intervals that you're actually returning here?
So we did a normal model for our prior. From that, we drew rates. We drew marriage rates, and then from those marriage rates, we drew Poisson.
Okay.
So we did inference on the rates, just because we probably could have just done it on the Poisson, but it was a little easier to visualize.
Okay, so tell us a little bit. Sorry, because I couldn't. Yeah, because it's not like drawn over here. But can you just describe the model again?
Sure.
Mm-hmm.
So we had a normal prior
For what?
for like the base of for the beta parameter of a gamma.
What's gamma? So can you go from like the data model first and then do a step by step? Yeah. So the data model is Poisson.
We drew the rate parameter for the Poisson from a gamma.
Mm-hmm.
And then we counted each year as its own group.
Mm-hmm.
And then we pulled the rate for each year
Mm-hmm.
from a normal.
Okay. So I guess this is the biggest different one across the board. So give me a second. I just want to bring up the iPad real quick so I can show the model. So again, hierarchical modeling, you can actually do it with different types of variables, of course, but and then different type of data. So here, I guess the biggest difference here is that the data model that you're doing is a Poisson instead of a normal. So why is that?
So we wanted to look at individual years
Mm-hmm.
instead of, I think it struck us that if you break the data into three groups of before, during, and after World War II, and then put priors on each of those groups,
Yeah.
that is kind of artificially creating a difference between.
Mm-hmm.
It's coercing in some ways a difference, I think. So we wanted to look at the individual years to see if we could model each individual year, and then if there was going to be any significant variation between years that would sort of naturally form those groups.
Okay, so I guess first of all, right, so like, okay, two differences I can understand. One is that you're having the data model to be a Poisson, and the other one is you're still treating each year independently, or like I said, separately.
Right.
Yeah.
Well, because if we treat each year separately, we can't do a normal modeling. So it doesn't make sense.
What do you mean?
Well, so I think if we have each year as its own group, and then we're doing a normal model based on one observation, that feels not right.
Okay, so first of all, can you draw it? Like the model, I mean, the way that you set up your hierarchical modeling, and you're a much better iPad user.
Putting the pressure on. Oh, wait,
Data
this is really thick.
It is very thick, yeah.
Okay.
But you cannot change it, I think that's it, yeah. So first of all, I do want to talk about the data model first. Because most of the people were doing normal, which is what we have seen before. And this group is doing a Poisson. So my guess is you're doing Poisson because you see counts, right? So you see counts in the data. So again, I mean, I think there are different ways that you can approach this. First of all, the original data, because first of all, the rates, it's raised per 1,000 people. So the original data actually is not integer. Okay, there is some, like, I mean, because it's out of 1,000 people, but I change it to be integer in this case, just to like say, like push people to think a little bit about, I mean, of course you can still approach it using a normal, but I kind of agree with Eli's group in this case that if you only get integer counts in this case, you might want to still do hierarchical model, of course, but you might want to use Poisson gamma instead of the normal that we have seen before. Okay, so let's see what the model looks like over here. Yeah, keep going. You can talk about it.
Okay. Well, so this is modeled by a Poisson. This is modeled by a gamma. And this one we already said is modeled by a normal. So.
All right. So the data model is Poisson, and you're still treating each year differently. And then And you're treating independent Poisson with independent rate.
Right. So we
Based
say
on-
there's some normal distribution,
Mm-hmm.
and oh, that's not very pretty. There we go.
Mhm.
And you pull rates
Mhm.
beta,
Mhm.
which is the rate parameter. We fix the shape parameter.
Right. Okay.
So you pull beta from here,
Mhm.
and then that determines the gamma that you draw,
Mhm.
which then determines the input into the Poisson.
Sounds good. So let me just fill in some detail over here. So in case you don't remember, gamma has two parameters, alpha and beta. So it looks like Eli's group you fix alpha. No.
Yeah.
Oh, you fix alpha. So this
Yeah.
is fixed.
We fixed alpha so that the rates would be reasonable, because we didn't
Okay.
want to be drawing
Mhm.
rates that were too high.
Mhm. And then beta, you put it in normal. So these are the betas you're talking about.
And we
Okay.
also centered the normal and then fixed the standard deviation of the normal so that we would be pulling reasonable rates.
Okay. So maybe I should change over here. So does it mean that it's not just alpha and beta, but it's alpha and beta I?
Yeah.
Okay. Because you're putting okay, so the hierarchy over here is that you have each data point still independently follow a Poisson distribution. And then each of the Poisson still has its own, fix the first parameter, the rate parameter. But the second parameter, again, will be group specific. Okay? And lastly, you draw a normal over there. Okay, so this is still a hierarchical model, of course, but this is taking into account that, first of all, it's counts. So we might want to do Poisson instead of normal. And then, of course, then for each, but keep in mind that you shouldn't do y1, say, until yn to the same, is this gamma?
Yeah, that was just the.
Okay, yeah, so let me just use lambda because it's just Poisson, like what people usually use, but I want to say that, keep in mind, the hierarchical model shouldn't be in this way, because if you put it into the same Poisson gamma, you are not allowing lambda to change. Oh, sorry, Poisson lambda. You're not allowing lambda to change. So what this is doing is what is yi iid from Poisson lambda. Yeah, go ahead.
Could you have done it so instead of
Mhm.
having a different lambda for every single
Mhm,
year, could you have done so they're just three lambdas?
Yes, so that would be another thing you can do, right? So the three, okay, so Tony's point is, instead of doing it one by one, because you still want to combine them in some way, I will do, okay, so y1 until yn, and then, so I guess y1 to y4 or something, gonna form, I should do it this way, sorry. Will be, I'm using lambda over here, lambda 1, and the middle ones will be lambda 2, and the last ones will be lambda 3. And then, of course, each of this will have its own further hyperparameters. Yeah, Nick? What do you mean by one layer? Like this part? Okay, what do you mean by, I think if you want to remove, there's only one you can remove, right? You can remove beta, but not gamma. You still need gamma to be there for the rate parameter, no? Okay, so here, yeah. Okay, so Eli's point or Eli's model is that you have the data in this way, right? And then each of this is a Poisson with rate parameter gamma. And then, so the one extra layer I think might be a little bit redundant over here will be that you're having extra beta. Because you still have a group, like group specific beta over here. I mean, you can do it, but you have more parameters to estimate. And it probably makes sense to just have one unified beta, which is a normal, for example. That will be another thing you can do, right? Okay, cool, yeah, so I guess, yeah, so for the hierarchical model over here, because it's counts, so you might want to do a Poisson, but you shouldn't do a Poisson with the same lambda, because this is saying that all of the rates are from the same Poisson distribution with the same rate parameter. But as you can see in the data point, just like we won't put in the same normal in this case. If you're doing a Poisson, you might want to do either what Eli did over here, a group, or not a group, year specific lambda I, or like what Tony said, instead of like 12 or 16 data points that you're like, 16 different groups that you're trying to do, you do 3 based on the before, during, and after that you can do, okay? And then of course earlier here, whether this layer is necessary probably depends on how you're gonna run the model, and then as well as do it to see the results, okay? So one last thing I want to talk about before we move on is, so actually there's well-studied approach to this type of problem for the hierarchical Poisson. So it's actually, I try to call it gamma Poisson. I will post this online because I tried to do something with it. And so it's going to be gamma Poisson hierarchical model. And it's widely used in the sense that you're having very different rates in your data, and you might want to do it in a hierarchical way, okay? So a hierarchical representation of all of this will be, I would say, okay, Y1, Y2, yn. So we're gonna do lambda 1, lambda 2, and lambda n over here. And this lambda is, so any yi is follow a Poisson lambda I. Okay, so this is very similar to what Eli's group did. It's pretty much, yeah, I should say it's the same. Yep. So the data model is still Poisson, but it's going to be a year-specific Poisson. Okay, and the difference is how to put the hyperpriors for those lambdas. Okay, so this one, any lambda I will still be a gamma, because that's conjugate. We learned about this Poisson gamma before that, so using conjugate will be easy, but again, once you put everything in JAGs, it probably doesn't matter, but let's keep using gamma for now. So here, a standard practice is actually having the 2 parameters, just alpha and beta, and the standard practice is putting 2 different gamma for these 2 parameters, because these 2 parameters needs to be non-negative. I should say they need to be positive. Okay, so that's why it becomes a standard practice that the people actually to put gamma on those parameters. So the model, if you write it, so let me, okay, so the last 2 lines of the model will be alpha from a gamma, say AB, and beta from gamma CD, something like this. Okay, and then you you let JAGs run to see what the results are. Okay, so this is pretty widely used in kind of hierarchical, like if the data arises in that way, this seems to be a pretty well-known method that people try to do. Okay, but I do agree what Tony and some others were saying earlier, that, and also like most of the methods that people have been doing with the normal case as well, that I can break it into 3 different periods. So instead of a year specific, I'm doing like a period specific, and then but then things will pretty much work similarly as well, because again, it's going to be a gamma, and then if you want to further make inference about the alpha and beta parameters over here, just put 2 more gammas over there. Okay, so I did write up something, and I will share that. I will post it on Moodle soon after class, so you might take a look at like the code, I didn't do any kind of analysis after getting the draws, but I'll leave that for you to explore if you want. Okay, but again, doing the normal is not wrong. It's just maybe not the best choice over here. Yeah, Nick?
See some data, right?
Mm-hmm.
And how can you tell that each observation comes from a distribution with a different parameter?
You cannot tell. Yeah, so in this case, so this is actually in the model that you decide, right? So yeah, so good question. So Nick's question is, how can you tell that the data actually, like each observation, so y1 to yn actually arises from a different distribution? This again is actually part of your modeling. That say the earlier stuff that I showed on my laptop before about like the plot of those rates across the year, if that's what you believe, and then you think that we should treat all of the years separately, you can still do a hierarchical model like this. But some people were concerned about like each year to be two separate, and instead of doing years, you're doing periods, and that's totally fine as well. Make sense? Okay. Yeah, so you don't know, and that's your assumption. So think about like moving forward, any kind of analysis that you're trying to do with not even Bayesian methods, any kind of methods, frequentist as well, you really need to think about the assumption that you make. So here, the stuff that you're doing is you're treating all of them each year to be separate, and then that's why in the hierarchical model, you're gonna have all of the rates separate in their own year. Okay? All right, cool. So I'll post that, and then you can take a look to see what you think. And okay, all right. So lastly, let me start talking about should be quick because I only have the model specification for the regression that I want to show you for today. So on Wednesday we can pick up from it. All right. Okay, yeah, we only have about 10 minutes anyway, so I will show you the general setup. This one mostly about like how the model is set up, and this is actually true for both regression in within like inference with frequentist methods and Bayesian methods. Just want to introduce the multiple linear regression. Right. So first of all, when we're trying to do regression, linear regression in particular, you usually have one response or independent variable y, and then you have multiple predictors. Okay, so here I'm using the generic P predictors over here. So the goal I listed over here, 3 goals over here. So first of all, you actually think about the model that we're gonna see it like soon, but you probably have seen it before. You're really trying to explore the conditional distribution of y given x. So y is the response, and x is your predictors, sometimes called covariates. Okay. That's the things that you want to use to explain your response, okay, in terms of a function. So it is a conditional distribution. And in particular, the linear regression is working on the mean of y. We're gonna see it in a minute, but I just want to highlight that you're talking about the conditional distribution, but the way that we specify the linear regression is through the mean, okay? And lastly, people actually want to make predictions of y given, like when you have new covariates or new predictors. I should say, same predictors, but from different observations coming in, you might want to make predictions based on that. Okay, so let me show you what I mean by actually looking at the mean of y as a function. So usually, this is what you will see. Okay, so yi being the observation I, and you have n different observations over here. So you're gonna write fxi, which is what we're talking about, the function of xi, and then plus some error term. Okay, so the error term, we usually specify independent errors. Okay, it might be from sampling error, from measurement, from lack of fit, etc., etc. So if you have done any kind of regression in the frequentist sense, you realize that once you have done all of that, you will check the goodness of fit by looking at how the errors are distributing. Okay, so that's all based on the assumption that we believe the observation is not just a linear function about all of the xi. There is some error or some up and down, some random unknown quantities that are being added to the response. And then, so that's why once you fit the linear regression, you actually should check whether all of the errors are actually behaving in the way that you thought. So that's the diagnostics that people usually do. Okay. All right. So the regression function, if you think about it, it's all the expectation. Okay. So this is the model setup for any regression. And usually you will see that people are going to assume a normal error for the, a normal distribution for the independent errors. and they center at 0 with some variance. So usually for linear regression, this is another quantity that people try to make inference about. Okay. Yeah. But if you do this, I just want to maybe like emphasize a little bit about the expectation over here. So you have yi, and if the error term is a normal center at 0 with some variance, then if you know that the relationship of yi and x and and epsilon I are in this way, you will know that the distribution of yi gonna follow normal centered at this, because it should be this plus the 0 mean. Okay, so you're gonna have fxi and then sigma square. Okay, so when you're doing regression, this is actually, so we call it regression, but it's really this particular model that you're trying to do. Okay. All right. So, but of course, you've seen like maybe simple linear regression, multiple linear regression. Things will get different if you move to single to multiple, especially in the frequentist estimation methods. But in terms of the Bayesian, let me just put it in the setup one more time, maybe with a simpler situation where you only have 2 predictors. So your response I, and then you have 2 predictors. Here I'm not putting any intercept, so any effect would just go into the error directly. Okay, so that's why you're gonna have a sigma square over here. So this is example of using 2 predictors in your multiple linear regression in this case. So the notation here, yi is the response for observation I, and xi1 is the value of the first predictor of the I observation, and xi2 is the second, the value of the second variable, second predictor over here. So beta 1 and beta 2, we call it coefficients, because you will see that a lot of times when you return results from R program or any other software, they make inference about beta. Okay, these betas are, think about it, beta 1 will be the effect of the first predictor, beta 2 will be the effect on the second predictor, etc., etc. Okay, all right. So first of all, when you're thinking about a multiple linear regression, you're really thinking about all of the predictors as a combo. Okay, it's all of them together. Say in this case, it's 2 of them. Okay, so you're thinking about them as a combo. So if you take the mean, you're looking at beta 1 times x1 plus beta 2 times x2 because of the way that you set up the model. Okay, so that's why if you try to understand the model itself, it's for any x, which is in this case 2 variables, x1 and x2, you will have expectation of y given x to be the sum of these 2 products over here. Okay, and another point to understand the model is that the variance of y is constant because you only have this only error term over here, epsilon I. So the variance of y given x will be sigma square, okay? Because this is deterministic, okay? This is just a function of all of the x over here. Okay? Yeah, so lastly, that's what I was talking about. If you actually fix this, the deviations of y will just be, because it would be all of the error terms, so it's going to be the normal 0 sigma square that you're trying to make inference about. Okay, all right, I think time is up, so I have to stop here. But yeah, so Wednesday we're going to come back and talk a little bit more about this. And also, we don't have a final exam, but we have a second midterm. And it's going to be a week from today. It's going to be in the evening time again from 6 to 9. I will write it for about an hour and a half, and you can take up to 3 hours to take it if you want. I'm going to make this just open book, open notes. Okay, so you don't have to prepare a cheat sheet. You can bring anything with you, any kind of notes that you have done before. Okay? I will send an email about this, so don't worry about it. Oh, sorry, yeah. It's up to, let me send an email. Yeah, I just need to think about it. Yeah, yeah. But definitely, sorry? Yeah, there will be a take home, but I need to figure out the time and deadline and stuff. Yeah, so if you have time conflicts, let me know just to reschedule.
I have a lot of instead of these big presentations.
Oh, okay. Yeah, so we can figure out. I mean, because before I was trying to meet the drop deadline to get the grading down, but now we don't have the pressure, so I'm happy to extend it if you want. Sure, yeah. Sounds good, because you're busy the entire afternoon, right? I mean, if not, I'm happy to do it. Okay. So send me an email. Monday morning should work. I don't have anything scheduled yet. So I'm free before 12. Maybe before 11:30. Okay. All right. Take care. Yeah.
I will have the same conflict on my
Oh, yeah? Okay. Oh, that's true. So send me an email. Let's do Tuesday. Okay, just like before.
Another question, I sent you like
Oh, yeah, I saw it. Yeah, yeah.
if you want I can print
Yeah, if you can print it,
Yeah, I
yeah,
will
that'll be good. And just leave it
you
at
will
my
be
office.
in your
Yeah, if I'm not there, just like tuck it over. Okay.
Super quick question. Does
Yeah.
not need an answer now.
Can I just close
yeah.
it?
If the